Hello, and this is my 2.2 assignment of steady state exercise. What is steady state exercise? So steady state exercise is where exercise intensity stays the same, and according to medical dictionary, activity that achieves a balance between the energy required by working muscles and the rate of oxygen and delivery of aerobic ATP production. Steady state exercise on each opponent. The heart rate increases with any movement due to the proprioceptors detecting movement, which sends a message up to the nervous system to the medulla oblongata, which then sends a signal to the SA node to increase the heart rate. Before the exercise even starts, there will be anticipatory rise when there is the adrenal gland releasing adrenaline. A chemoreceptor detects the adrenaline in the bloodstream and sends a message to the SA node to increase the heart rate. The heart rate will increase initially to the reaction of exercise and will plateau as there is enough oxygen to meet the criteria of the exercise. When the exercise ends, the heart rate will significantly decrease as there is little oxygen depth from working aerobically. Stroke volume. Stroke volume is the amount of blood pumped by one ventricle in one contraction. The stroke volume will increase gradually and levels off when it reaches its maximum, and will slightly decrease and due to the intensity of the exercise staying the same and plateaus after a couple of minutes. The average stroke volume is 70 to 80 ml, while a trained athlete can be 110 ml. Venous return can impact the stroke volume. Venous return is the return of blood to the heart after it has been distributed to the body. The venous return will gradually increase and plateau. After the steady state exercise stops, it will rapidly decrease due to the heart pumping blood at a slower rate. Starling's law. Starling's law states that stroke volume increases in response to an increase in blood volume filling the heart. The ventricle wall stretches, which causes the heart rate to contract more forcibly. Therefore, in relation to Starling's law, when there is a decrease in contractions and the amount of blood filling in the heart, then the stroke volume decreases. Cardio output. Cardio output is the volume of blood pumped out of the heart in 1 minute. It's equal to the heart rate multiplied by the stroke volume. It is dependent on the heart rate and stroke volume, so it will increase and plateau as the heart rate and stroke volume does. There isn't an increasing demand of oxygen due to it being submaximal exercise. A typical adult rest is 4,900 milliliters during moderate exercise. The total cardio output would be 17.5 liters. During exercise, there will be an increase of amount of blood supplied to the muscles as they need energy. Mo Farah's cardio output at rest will be 3,630 milliliters, while during exercise it will be 4,400 milliliters. This shows that cardio output is high due to the fact they can pump more blood in a greater volume. Blood pressure. Blood pressure is the pressure of blood against the walls of the arteries, which has resulted from two forces, one being the heart pumping to the blood into the arteries, and the other force is the fall of arteries as they resist the blood flow. The systolic pressure is the pressure exerted in the arteries when the heart contracts, and the diastolic pressure is the pressure exerted in the arteries when the heart relaxes and fills blood. During steady state exercise, there will be a slight increase in systolic blood pressure and the plateau, while the steady state exercise stops. Pressure will rapidly decrease due to the heart isn't pumping blood, which much loss. The diastolic pressure would either stay the same or slightly decrease. This is due to vasodilation. Blood flow. There is an increased dilation in the arteries in the active muscles, which is called vasodilation. This involves the blood vessels diameter to increase when there is an increased blood flow to the muscles. This happens during steady state exercise as the muscles need more blood for energy due to the higher cardio output and stroke volume to the working muscles. Therefore, the blood flow has a stronger force. Vasoconstriction will occur when the diameter in the muscle fibers in the vessels will decrease. Also, muscles increase the blood flow due to them squeezing the veins around the body. Breathing rate. Breathing rate increases as the exercise intensity does due to the demand of oxygen required for the aerobic exercise. The breathing rate will plateau after. Once the exercise stops, there will be a rapid decrease in breathing rate due to the small oxygen debit, and there isn't any wasteful products to flush out. Tidal volume. Tidal volume is the measure of amount of air a person inhales during a normal breath. There will be a gradual increase in tidal volume due to the working muscles requiring more oxygen and the increased resistance, and therefore is a higher concentration of oxygen required in the blood. The tidal volume will plateau due to the criteria of oxygen needed in the working muscles are reached. There will be a rapid decrease in tidal volume as the amount of air needed in a single breath has decreased, and there is less oxygen needed for the working muscles. Also, there's no wasteful products that need to be flushed out. The oxygen desiccation curve. Oxygen desiccation is the amount of oxygen that is released from the hemoglobin that will diffuse into the working muscles. The oxygen desiccation curve is a graph that shows the relation between the percentage of oxygen saturation of blood and the partial pressure of oxygen. During steady-state exercise, there is an increase in temperature and lower pH concentration, affecting the oxygen hemoglobin desiccation curve, which oxygen can be given to the active muscles. An overview of the aerobic system. The aerobic system works anaerobically and happens in the mitochondria in the muscle cells. This system provides two phosphate molecules and the byproduct acetylcholine CoA. It uses glycogen in the cells. However, when the glycogen runs out, it starts to use the fat. The lipase breaks down the fatty acid, which turns into acetylcholine CoA, which we use in the Krebs cycle. The energy provided in the aerobic system are majority used for high duration and moderately intense exercise. The second part of the cycle is the Krebs cycle. This provides a continuous supply of electrons to feed into the electron transport chain, which is the third part. Acetylcholine CoA combines with oxalated acid, which creates citric acid, which goes into the Krebs cycle. The Krebs cycle produces carbon dioxide, oxalated acid, and two molecules of phosphate, which allows to re-synthetise the process of adenosine phosphate and hydrogen. The electron transport chain is where hydrogen combines with NDA plus FDA, which gives you NDH plus FADH, the electron transport chain. The electron transport chain occurs in many crystin in the mitochondria. The positive hydrogen is deposited during the electron chain to combine with oxygen to form water, and the negative hydrogen ions simulate the 34 molecules. Muscle spindles. Muscle spindles are proprioceptors found in skeletal muscles. They are activated when a muscle stretches, and this indicates initiates a reflex that resists the stretch. The primary sensor senses in the muscle spindles, and when they detect a stretch, responds to the velocity and degree of a stretch. The secondary sensory senses detect and sends the information of the degree to the central nervous system. During steady state exercise, they become more efficient transmitting the information. Golgi tendon organs are located in the tendons. Like muscle spindles, they detect the stretch of a muscle, but rather than the angle, they detect the strength of a muscle contraction and send this information to the central nervous system. Both components work together to make a smooth movement. Now, with my hypothesis with doing this experiment, I believe that the heart rate will increase initially before the exercise due to the anticipated rise, and during exercise it will plateau after 3 minutes. Post though, it will return to resting heart rate as there is no wasteful products. The systolic blood pressure will increase before it plateaus after 3 minutes after its intensity stays the same, but the diastolic will stay the same. The blood saturation will be 98 to 100 pre-exercise, but it decreased due to the oxygen being consumed by the muscles. Breathing rate will initially increase during exercise, but will plateau after 3 minutes due to the intensity stabilizing. Post-exercise, it will return to normal due to there being no wasteful products. The aerobic glycolic will be used during steady-state exercise, which means no lactic acid will be produced. Our method is here, and this is where we ideally would like to monitor each component of the steady-state exercise in this experiment. Now, looking at these graphs, the heart rate before the exercise starts, there will be an anticipatory rise due to the client's emotional release of norepinephrine, which stimulates the release of adrenaline and indicates the SA node to increase the heart rate. However, during steady state exercise, as we can see, the heart rate will initially increase significantly due to the intensity of the exercise and will plateau after the demands of oxygen are met. This is shown by the experiment when looking at the average heart rate for 3 clients. The heart rate increased in the times 4, 1, 4, 10 and 17 and post 1 minute. As you can see on the second graph, their beats per minute increased by 9.2, 9.8 and 9.8 and decreased by 9%. Therefore, this shows in the 1 to 4 minute there is a bigger percentage rate than in the 4 to 17 minutes, which shows that the heart is starting to plateau. Arguably, though, the percentage is too high for the steady state exercise, so the reason why this doesn't match up could be due to the experimental effort looking at the Borg scale, which we can see from the 2 clients that their RPE increases, which supports the increase in heart rate due to the body's demands influence of clients. However, looking at Evelyn's RPE, this doesn't reflect her heart rate, so it can be suggested that she was working hard as she should have been. To back the statement up, that she wasn't working as hard, her O2 saturation levels stayed the same until the 30th minute, and after that decreases from 67 to from 100 on the 80th minute, showing that her working muscles only needed oxygen later in the experiment, as she wasn't working hard enough for the oxygen criteria. If the method had gone according to plan, then the data would represent our hypothesis by the heart rate plateauing after 3 to 4 minutes, decreasing after exercise had finished. Analysis of the O2 saturation. The normative data states that oxygen saturation should be decreasing during steady state exercise because oxygen in the blood is being used up by respiration. The best representation of this is Evelyn's, who O2 saturation levels stayed the same until at 99 until the 30 minutes when began to decrease before reaching 67 at the 18th minute. This is a decrease of 67.7%. Morgan's O2 saturation decreased continually between minute 1 before exercise and then minute 10 from 99 to 96, which is a 3% decrease. However, from 10 to 20 minutes, it went back up to 98, and that is a 2% increase. This is likely because Morgan was working above steady state exercise between the 1st and 10th minute, so more oxygen will be used up. This also may be the reason why Ocean's oxygen concentration in the blood increased from 96 to 99 between 11th and 16th minute. Now, looking at the Borg scale, the normative data states that at working 60% of 60 to 70% of heart rate, there should be a RP level of 10 to 14, which, looking at the clients, their data is in that range. The client's RPE should increase in the first 3 minutes, which we can see from all 3 clients. However, analysing the initial start of the exercise is quite hard.